Listen up, here's the story about a little guy that lives in a blue world. And all day and all night, and everything he sees is just blue. Like him, inside and outside. Blue his house with the blue little window and a blue Corvette. And everything is blue for him and himself and everybody around. 'Cause he ain't got nobody to listen.
Hi. Okay.
I'm blue, I would need, I would die, 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 I would need, I would die. I'm blue, I would need.
So for our roller coaster that has no vertical loops, we went on Kingda Ka. So for the physics of Kingda Ka, the ride starts at rest at the beginning of a long straightaway that eventually leads up to the tall hill. When the ride starts, a large force is applied to the train so that it accelerates from rest to the ride's top speed at 128 miles per hour in just under 3.5 seconds. This quick and rapid acceleration allows the train car to have enough momentum, which is mass times velocity, to travel all the way up the 139-meter hill without any external forces acting on it, aside from gravity and friction from the wheels on the track and from air resistance. The train car's kinetic energy is at a maximum at the moment it reaches its top speed of 128 miles per hour, and its gravitational potential energy is the highest the moment it reaches the top of the hill. Throughout the ride's duration, energy is not conserved due to the presence of external forces like the force of friction. So the law of conservation of energy cannot be applied to this ride. Then finally, once the train car reaches the top of the hill, it then goes downhill at almost an angle of 90 degrees, and the car rapidly accelerates. But since energy is not conserved, we cannot use the law of conservation of energy to find the velocity at the bottom of the hill.
Physics. Physics.
The next ride we chose was the carousel, which exhibits circular motion. A person on the ride would sit on a horse or an animal of their choosing, which is attached to poles, which is then attached to the carousel. When the carousel begins to move, it demonstrates circular motion. As the carousel speeds up, the rider experiences a few different forces. One force is the force of gravity, and another is normal force. But a third is centripetal force. Since the person riding the carousel experiences centripetal force, they are therefore experiencing centripetal acceleration. The centripetal acceleration is equal to the velocity squared over the radius. This centripetal acceleration is pointed towards the center of the carousel. But the rider's velocity is in the direction that they are moving, tangential to the circular path. If the rider's horse was somehow to be released from the carousel, in theory, it would continue in the direction the velocity is pointing instead of continuing the circular path. The horse's path would be tangential to the circular path of the carousel.
And all day and all night, and everything he sees is just blue, like him.
Hi, I'm Zach, and this is Cody, and welcome back to the Disney Channel. Dun 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 dun.
Inside and outside, blue his house with the blue little window and a blue Corvette, and everything is blue for him and himself and everybody around. 'Cause he ain't got nobody to listen. I'm blue, I would need, I would die, 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 I would need, I would die.
at Six Flags with multiple loops is the Ride Batman. And the physics behind a loop is that at the bottom of it, the kinetic energy is the max, so that the cart has the ability to go up and over the loop. And at the bottom, the normal force and gravitational force are equal, so the cart accelerates in the x direction from the applied force. At the top of the loop, the potential energy is the greatest, and the forces at the top of the loop are gravitational and normal, which both point downwards, causing the cart to accelerate downward and gaining more kinetic energy. Because the energy is conserved on a roller coaster, the potential energy at the top of the loop, which is the mass times the gravitational constant times the height of the loop, is equal to the bottom of the loop, which is kinetic energy, which is 1/2 times the mass of the cart times the velocity of the cart squared. Knowing all of this, you are able to find the velocity and height of the loop and the cart at the top and bottom of the loop. And the forces at the top help you to figure out the acceleration of the cart at the top and bottom of the loop.